Hello all. I hope you are having a good time. So welcome to this deep dive into the fascinating world of CNNs or convolutional neural network. So by definition, if at all I have to explain what is a CNN. So CNN is a convolutional neural network, which is a class of deep learning neural network specifically designed to process and analyze visual data. They are widely used in computer vision tasks such as image recognition and object recognition, and they have this very unique ability to adaptively learn from a spatial hierarchies and features from an input image. That's too much of a technical definition, I know. So let's try to understand and break down this CNN in a much more granular level, and let's try to understand what goes inside this CNN and why CNN is so powerful. To understand the concepts of CNN, we first need to decipher some concepts, which are: what are strides, when do we use a stride, what are kernels, and what are padding, what is max pooling and average pooling, and when do we use all of these. These concepts will help us dissect the internals of CNN in a much more lucid way. So let's first understand what is a stride. So strides technically means the step size with which the kernel moves across the input. A stride of 1 basically means the filter or kernel will move 1 pixel at a time. Kernel here means nothing but this filter. So you see filter here, it's a 3x3 filter. At the end, it's just a matrix with some values inside it: 0, 1, 5, 8, 1, 1, and 1, 1. So if this filter is going to convolve with this matrix here, and the programmer has specified the stride as 1, it simply means it will move 1 step at a time. And at the same time, if I have specified the stride as 2, it will move 2 pixels at a time. It's very easy if you see or try to understand the concept of filter and strides by this figure. At the end of the day, this is just a matrix, and around this matrix, this is the kernel or filter. This filter has to move around this matrix through the sliding window approach. If I have specified the stride as 1, it will move 1 pixel, and if I have specified the stride as 2, it will move 2 pixel at a time. If I will specify the stride as 3, it will move 3 pixel at a time. But hold on, the moment I will specify the stride 3, it won't go. There is no space for here to cover it. Now let's try to understand how do we tackle this issue. Let me explain you the issue once again. If you specify a stride equal to 2, so let's suppose we have this matrix here which is 5x5, and let's take a kernel which is of 3x3. So, and our programmer has specified the stride is equal to 2. So ideally, the moment we specify a stride 2, the kernel using the sliding window approach will move 2 pixels. So that's how it's going to happen. So it will move 2 pixels on the right side. But the moment if it wants to take another step, that means the next pixel should be here somewhere. So it should start from here, and it will need 2 extra pixels here. But there is no space here to move it. Ideally, we should have 2 more pixels here. But since it's not there, using sliding window approach, again this kernel will move here and it will start from downside here. But if this pixel has some important information, this will be lost in this process. Now to avoid this conflict, what we will do, we will add extra pixels at the end of our image or our matrix here. These pixels will contain the value 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and we will add it on both sides, not 4 sides actually. So on all 4 sides we will add this padding. So this is how it will be. You see this matrix here, and when we say padding is equal to 1, there is 1 extra layer added, and when we say padding is equal to 2, it will add 2 layers on top of it. So padding refers to adding extra pixel around the input image, which helps preserve the spatial dimensions of the output after convolution, like this. So if we have padding is equal to 1, we are gonna add 1 layer around the image, and if padding is equal to 2, that's how it's gonna look like. Now depending on what we need in what situations, we can add padding as we need it. but we have to be very careful at it also increases the size of image and computation. So be very careful in adding padding, and there are many scenarios in which we don't need padding at all. So this is what padding is. Now let me explain you what is max pooling. So by definition, max pooling is downsampling operation which is commonly used in CNN, and the primary purpose here is to reduce the spatial dimensions of input feature map. That's too much of a technical terms in a single definition. Now let me try to explain you through a simple example. Now let's suppose we have this matrix here which has all the values 1 4 5 8 7 8 9 0 and not all, and we have this filter which is 2 cross 2 filter, and I have mentioned the stride is equal to 2. So these two are very key factors in our max pool operation, the filter size and the stride size. What is the meaning of a stride? I have already explained. It just defines how much step you want to move, and the filter here is a 2 cross 2 filter. So if I have to apply max pool operation, first of all we are going to take this. So this is a 2 cross 2 part of this matrix, and we will be using stride 2 using a sliding window approach. So next time we will take this part of the matrix. So let's first concentrate on this part. So we have in this part 1 4 5 8. So along all of this we will be taking the maximum of it. So here is 8. So out of this we take here and we will create a new matrix which will contain 8. Again similar operation on this 7 8 9 0. So maximum value is 9, so we will take 9 here. Similarly here maximum value is 8, so we will apply 8 here, and here maximum value is 9, so we will do 9 here. So this is our final matrix. In real-time scenario, this will be an matrix which is going to represent an image. For example, if this is an image which is 4 cross 4, I'm taking a dual size image, dual channel image basically, and if this is the matrix which represents the image, and these are the values inside the image. So if I apply a max pool operation on top of this image using a 2 cross 2 filter using sliding window approach on every part of 2 cross 2 part of this matrix, choose the highest value and I will supply it and create a new matrix. So this is what max pooling is. Technically, this process helps us in two main ways. It reduces the computational complexity for the following layers and helps in control the overfitting by providing an abstract form of representation. It's really important part because in a convolutional neural network, max pool layer and convolutional layer, it's said to be create one layer. So they are usually used in combination. Next, what we are going to look at is what is a convolutional operation. The primary purpose of convolution is to detect patterns and edges, textures, or more complex features in an input image. Usually in an ideal scenario, one layer is not enough to detect all the patterns in an image, so we will add multiple layers and multiple kernels. Now to understand convolution through an example, let's see through this example here. Suppose we have this matrix here which is a 5 cross 5 matrix. Let's assume this matrix represents a dual channel image and the values inside this are the pixel values. So 7 is a pixel value, 2 is a pixel value, 3 is a pixel value here. Now to do a convolutional operation on top of this, we have designed a kernel here which is a 3 cross 3 kernel. Here it's a 3 cross 3 kernel, and if we want to do a convolution operation on top of this matrix here, every element of this matrix is going to multiply to all the elements, the pixel values basically of this matrix. It's simply a matrix multiplication which will be something like this. So for the first value here which is 6, this is how we are going to achieve it. So 7 into 1, so this is 7 multiplied by 1 plus 4 into 1, so it's like 4 into 1 here. Similarly, every element is multiplied like a simple matrix multiplication, and at the end we will get this value here. Now this operation will continue for each and every pixel value here. For example, the kernel value is 3 cross 3 here, so and a stride, let's suppose, is equal to 1. So the next value is, so let me select a different color. So the kernel will start from here till here, and whatever value we will get it from here, it will come here. Okay, let's choose a separate color. It's not, yeah, it will come here, which will be 7, I guess. You can do the mathematics. It's pretty simple. It's a simply matrix multiplication. So similarly, if we multiply a 5 cross 5 matrix with 3 cross 3, the output will be 3 cross 3. So to know the actual output of the feature map, there is a formula which we are going to use, which I'm going to show in further part of this video. But for an ideal scenario, whenever we do a 5 cross 5 matrix which represents the image, and we usually for that scenario we use a 3 cross 3 kernel, the output size is 3 cross 3. Now let me give you the formula. So this is the formula which will help you to get the output shape after each and every operation. For example, if we are applying a convolutional operation, this is the formula which will give you the output shape. And if we are applying a max pool operation, this formula will help you to get the output shape if you want, where M represents the original size of the image, N represents the filter size, P is the padding, S is the stride. Stride basically means how much you are moving, how much step you are moving basically. This is the depth. For example, if I have an image like in earlier example, I have a matrix of 5 cross 5 shape. So this would be the original shape of the image, which is M. So M here is 5. Let me write it down here. And if we are applying a kernel of 3 cross 3 on top of this matrix, so in that case our N size is 3, padding is 0, stride is 1, and depth is 1 as well. So the final output would be 5 minus 3 divided by 1 plus 1, which is equal to 3. So our output shape is a 3 cross 3 matrix if we are doing a convolutional operation on top of it. Now to understand it in a more detailed way, let me take you through an example of how we actually apply a convolutional operation and a max pool operation on top of an image. So here is our image. So let's suppose I have an image of 64 cross 64 cross 3. Here 3 represents that it's an RGB image. That means it's a 3-channel image. So on a 64 cross 64 cross 3 image, I am applying a convolutional operation with a filter size of 3 cross 3 here, where number of filters I am using is 10, stride is 1, and padding is 0. For our simplicity and convenience, I have written the formula here so that we can refer. Now to know the actual size of after this convolutional operation, let's apply our formula, which is M minus N plus 2P by S plus 1. So here our M is where? Here our M is 64. There you go. And our N is 3, which is our kernel size 3 cross 3, plus 2 into 0. 0 because our padding is 0, divided by 1 because our stride is 1, plus 1, which is equal to 62. So our output size here is 62 cross 62, and D is depth, which is number of filters. How many filters we are using? 10. So 60 cross 2, 62 cross 62 cross 10. So this is the output. Again, if we apply a max pool operation on top of it with a filter of 2 cross 2 and a stride of 2, we will apply same formula here, M minus N by S plus 1, which is 62, which is the actual size here. So actual size here is 62, and our N, which is filter size here, is 2, which is here, and divided by 2, which is our stride, plus 1 according to our formula, which will give us 31 in the result. Pretty simple, isn't it? You just, if at any point of time, if you want to know what would be the output size, you can just use this formula and it will give you more clarity on what output shape you are getting. It is very crucial when you are designing a lot of convolutional layers. It is very crucial to know what is the input size which will go to the other layer. Usually a combination of convolutional layer and max pool layer is considered to be one layer. in an ideal scenario. So whenever we design a lot of convolutional layer, there will be one convolutional layer, then will be one max pool layer which will be used together. And using max pool layer always reduces the size of image. So if at all in any part of your use case you don't want to reduce the size of the image, you don't have to use max pool at all. But using max pool ideally saves a lot of time and a lot of overfitting issues. So this is an simple example of what convolutional operation and max pool operation looks like on an image. In next part, I am going to show you a detailed architecture of how we apply a convolutional neural network on top of an image. Let me give you one more example of how a convolutional operation and max pooling operation is applied on top of an image, and then how it is flattened and connected to a dense neural network for an output y here. Now suppose we have a problem statement in front of us to identify whether this image is a dog or not a dog. So suppose this image is of a dog, and we want to train our model to identify whether this image or any future images whichever supply to this network is a dog or not a dog. So first layer here, if you want to do a convolutional operation, the filter size is n cross n, number of filters is 10, stride is 1, and padding is 0. So the output layer or the output feature here would be 62 cross 62 cross 10. 10 here is the depth, which is number of filters. 62 cross 62 we will get through the formula, which is m minus n plus 2p divided by s plus 1. Here let me change the color. So here m is 64 minus n is what is 3 cross 3 the filter size, and p would be 0 because we are having padding as 0. Stride will be 1. So this will be our output here, 62. That's why we are getting output 62 cross 62 cross 10. Let me just delete it. Perfect. So the moment we have got our first convolutional layer output, then we will apply a max pooling on top of it with a filter size of 2 cross 2. Stride is 2. So here the output is 31 cross 10. Again, because number of filters here is 10, this will continue here. Now here is the catch. Here our input feature is in n dimension. Basically it's in 10 dimension matrices. So every layer now it's getting converted here, or we will flatten the data inside the matrix into a flat array here, you see. So the number of elements in this array or flattened part of the matrix will contain, which is 31 cross 10, which is equal to 9610. So the first layer of neurons which we are going to design in our dense neural network or connected neural network would contain 9610 neurons. Then in hidden layer we can define our neurons as per our need, but since it's a binary classification problem, the output will contain only one neuron which will give us output either 0 or 1. 1 means it's not a dog. Sorry, 1 means it's a dog, and 0 means it's not a dog. That's how the whole flow of a CNN layer which is connected to a neural network is always happens basically. So let me explain you a bigger architecture where we will have multiple convolutional layer and one dense layer connected to it. So here ideally the combination of one convolutional layer and one max pooling layer is considered to be one CNN layer. So this is called one CNN layer ideally. So let me give you a one more depth example of how an image training or image identification or feature extraction happens in a CNN layer through one more example, or a more detailed example where multiple layers are involved. All right, so let us assume we have this image, a beautiful panda image, and we are going to create a convolutional neural network to train a model which will identify whether it's a panda or not a panda. So the process which involves in this whole training or creating the neural network, I am taking you through each and every step in detail way in this part of this video. So I would say the size of this image is 64 cross 3. It's a 3 channel image, that's why 3. and the length and width of the image is 64 cross 64. So to apply a convolutional layer on top of it, first of all we are going to define what is the filter. So filter size is 3 cross 3. Number of filters which we are going to use is 10, stride is 1, padding is 0. So the moment we apply a convolutional operation on top of this image using these variables here, the output size which we will get is 62 cross 62 cross 10. Why 10? Because number of filters here is 10, and 62 we will get once we use this formula m minus n plus 2p. So m in our case is 64 and n in our case is 3. So 64 minus 3 divided by s stride, which is 1, and again we will do a plus 1. 2p will be 0 because our padding is 0. So which output of this will come as 62. Perfect. So we have done one convolutional operation on top of this image. Once we apply a convolutional operation, again we will do a max pool on top of it. So moment we apply a max pool, we will get the output as 31 cross 31 cross 10. 10 as usual, number of filters will remain same. And once we apply a max pool operation, if you remember the formula m minus n by s plus 1, we will apply the same formula and we will get this output as 31 cross 31 cross 10. And there is one more factor here which we need to look at, the number of trainable parameters. So in first case, the number of trainable parameters will be 3 into 3 into 3. So the size of the filter 3 cross 3, and then the channel of the filters, which is 3. So 3 cross 3 into 10, number of filter is 10 plus 10. So for every filter we will be having one bias there, so which will give us the total trainable parameters as 280. Similarly, in max pool case, there are number of trainable parameters. Basically it will be 0. So a combination of convolutional layer and max pooling layer, this both part combines one layer. So this is one layer, and one more layer is, this is how it's going to look like. We will have one more convolutional operation with a filter size of 7 cross 7, number of filters 20, stride 2, and padding is equal to 0. So the number of trainable parameters, as usual, we will use 7 cross 7, which is the size of our filter multiplied by, there it is 10 multiplied by 10 and plus 20 for every, I would say for every filter you will add one more bias to every filter. So that's where we have done plus 20. So this will give you 9,820 trainable parameters. You see how with the size of filters and the number of filters, the trainable parameters are changing drastically. So the output size here will be 13 cross 13 cross 20. Again, after applying a convolutional operation, we will apply a max pooling operation. So max pooling operation will be of 2 cross 2 filter size, and stride is equal to 2. Number of parameters here as usual will be 0, because in max pooling layer we are not having any trainable parameters. We are just reducing the size of the feature image. And so in this case the output is 6 cross 6 cross 10. Similar, you can use this formula. For the sake of convenience, I have added it here, which is m minus n plus 2p. It's pretty much self-explanatory. Once you know what a stride is, once you know what padding is, and once you know how padding moves, how stride moves, and in what scenario which part to use. So this completes our layer 2. So let me change the color so that we are, so this is layer 2, so this is layer 1, this is layer 2. So the moment we have 2 layers, let's suppose just for the sake of convenience we need only 2 layers for this purpose. Then after this we will flatten all of this, I would say all of this matrix or nth dimension matrix into a normal array. And once we flatten the normal array, the total number of elements in that array would be 6 into 6 into 20. Because of here it's an n-dimensional matrix and we are going to convert it into a flattened array. So this will be the total number of elements in that array. It's simple multiplication. So the first layer here will have 720 neurons, and inside this layer you can define as many neurons you need depending on what situation you are in. And since it's a binary classification problem, that's why we have added only one neuron here, which will give us the prediction value, which in our case can be 0 or 1. And here we will also use a function which is sigmoid function or softmax function. Since it's a binary classification problem, we are gonna use sigmoid function here. But be very careful if it's a multi-class problem. Suppose instead of detecting one panda, if we have multiple animal use case, for example, we want to detect whether this is a lion, this is a cat, or this is a dog. In that case, we will have multiple animals. In that case, we will use softmax function here for the output layer. And the number of neurons here will be equal to the number of class we are going to predict. Then after that, we will calculate the cost function. And the idea of this cost function is to measure how much data we are losing in this process. And through a backpropagation channel, like we already know in artificial neural network, the backpropagation is used to balance all the weights throughout the network. We will use backpropagation and we will create the actual more suitable weights throughout the network, which in turn will give us a proper CNN layer. So this is an overall example of how a CNN layer looks like and how do we design a CNN layer. What are the different concepts, like when do we use convolutional, what is convolutional operation, what is max pooling, when do we apply padding, when do we apply stride, how number of filters play a role, and when do we flatten in n-dimensional matrix, of course. Hope this gives you an overall idea of how CNN layer works. Now let me summarize all the contents, whatever we have looked so far in this video. So first of all, we looked at what is a stride and how do we use a stride. So basically the stride defines the step size with which the kernel moves throughout the matrix using a sliding window approach. And what is a kernel? So kernel is basically also known as filter, which is a small weighted matrix. In most of the cases, we usually define it as a 3x3 matrix, but there are some cases where we use 7x7 or 5x5 matrix. But we have to be very careful that whenever we are using kernel, the dimension of kernel like 3x3 or 5x5, they will always be the odd numbers. They will never be the even numbers. There is a specific reason for this, but explaining that will go beyond the scope of this video. Just keep that in mind. And then next we looked at what is padding. So padding refers to adding an extra pixel around the image, which helps in preserve the spatial dimensions. Of course, padding is really helpful if you feel you are losing some sort of data around the edges of the image. You add extra pixels around the image. It's like adding a layer on top of it. Then we looked at what is max pooling. So max pooling is a downsampling operation commonly used in CNN neural networks. Max pooling is really important if your image size is really getting bigger and you want to downsample it. We have also one more approach we call it average pooling, where instead of taking the maximum value, you take out the average of that matrix in that case. Then we looked at the star of the show, what is the actual architecture of CNN and what is a convolutional operation, in fact what it is. So by definition, a convolution is a fundamental operation designed to extract features from input data, particularly in tasks involving image manipulation, recognition, or classification. We also looked at a bit of what functions we use when there is a binary classification and what function we ideally use when there is a multi-class classification. This is it for the current video. See you in next video. So in next video, I will talk about how you can create the CNN network using Python. We'll be using Keras and other TensorFlow libraries to create the CNN layer from scratch. So see you later.